Hi, welcome to a new session of control systems. In today's class 4, we are going to see the time response analysis, especially when zeta is greater than 1, that is overdamped system. So from our previous classes, we have seen that the overdamped system indicates that the zeta value is greater than 1. So you can see here we have a transfer function of a second order system where this is derived from the block diagram which is shown by this figure, and this is made to a simple system with damping ratio as zeta and natural frequency as omega n. And for zeta greater than 1, if at all you take the characteristic equation roots, you're going to get the roots of s1 s2, which is given by minus zeta omega n plus or minus omega n under root of zeta square minus 1. So here, just for a change, we are going to take the assumption that SA is a root which is equal to minus S1 and SB is a root which is equal to minus S2 for overdamped systems. So that you can take the value of SA here to be zeta omega n minus omega n under root zeta square minus 1. Similarly, SB a root which is equal to zeta omega n plus omega n under root of zeta square minus 1. So this we're treating as equation 2. Now take the transfer function, substitute the value of r of s as unit step, that is equal to 1 by s. Then c of s changes to omega n square by s into s plus a and s into s plus b. Now this is a partial fraction that can be solved with the help of this abc's. Get the value of a by substituting s equal to 0 in the actual partial fraction value. Then you're going to get the value of a which is equal to 1. Just substitute the value of SA and SB which we had taken from equation 2. Now, how to get the value of B? So B can be obtained by multiplying the transfer function with S plus SA and substituting the value of S is equal to minus SA. And what happens, you can see I have substituted the value of S equal to minus SA and I have substituted the value of actual SA. With this, the SA value, SB value, the like terms and unlike terms, you have to check it out and you have to cancel it. Then I'm going to remain with the value of B, which is here it is obtained to be omega n by minus SA into 2 times multiplied with zeta square minus 1. This I'm reading as equation 4b. 4a is the value of A, 4b is the value of B. Now after getting the value of 4b, on the similar basis I can get the value of C constant. Just you need to multiply S plus SB with the transfer function and substitute S is equal to minus SB. So here we have done that and we have obtained the value of C, which is quite similar to the equation of 4b. Here it is a positive term, here is a negative term. The B value is in negative form, the value of C is in the positive form. So with the equations 4a, 4b and 4c, I have substituted the values of a, b, c. In this equation 3, I am going to get the function c of s is equal to 1 by s plus minus omega n by sa into 2 times multiplied with this zeta square minus 1. To with this, we have the value 1 by s plus sa, because the original value here you can see s plus sa is there, and similarly you have s plus sb which is over here. Substitute the value of c. Now rearranging the terms in a proper way and making it to as equation 5 and applying Laplace inverse to this equation 5, then what I'm going to get? So I'm going to get the value here as 1 by s inverse value is 1 minus this omega n by 2 zeta by 2 under root of zeta square minus 1. This we're taking as a constant value. Then you have 1 by sa. The inverse Laplace of 1 by s plus sa will be equal to e to the power of minus sat. Fine. I hope you understand how we got this particular Laplace inverse value. Similar basis, you take omega n by 2 under root of zeta square minus 1 as a constant, 1 by sb as another constant, and applying Laplace inverse to this term 1 by s plus sb, we are going to get the value as e to the power of minus sbt. Now taking the common terms on one side, I'm going to get 1 minus omega n by 2 multiplied with zeta square or the under root of zeta square minus 1 to this fraction. Now this equation 6 is framed. Now substituting for different values of zeta, if it only substitute different values of zeta more than 1, then for the input r of t, I'm going to get the output c of t, which is obtained to be in this fashion for zeta equal to 1.5. What if I increase the value of zeta? If I increase the value of zeta, which is equal to 2.5 over here, the graph is obtained in this fashion. Similarly, when I apply zeta equal to 3, so the graph is obtained in this fashion. And as you increase the value of zeta, you can see the exponential rising curve, it is reaching towards the t-axis, that is x-axis. Okay, so this is how the behavior of the system would be for overdamped system. So let us summarize the overall second order system for different values of zeta. For zeta equal to 0, we had the transfer function which is omega n square by s square plus omega n square, and C of s is obtained to be omega n square by s into s square plus omega n square. For this we have applied the partial fractions, then we applied the inverse Laplace, and we got the value of C of t which is equal to 1 minus cos omega nt. Now this type of equation results in this kind of waveform, which is nothing but it is a repeated oscillations. So that is the value of C of t. Now what if case we have the underdamped system where the value of zeta ranges from 0 to 1. For that we have taken the transfer function, then we have taken the C of s value with R of s value is equal to 1 by s, that is the unit step input, and then for the same input we obtain the value C of t which is obtained to be 1 minus e to the power of minus zeta omega nt by under root of 1 minus zeta square sine of omega d t plus theta. Now for this kind of equation we got the output C of t which is shown in this particular waveform. You can say we have some oscillations but they are getting damped out and we are reaching to the value 1. So the initial the behavior was transient and later on the steady state conditions were reached. So damping out oscillations what is observed under underdamped system. Okay. Now when we have seen for the critical damped condition where the zeta value is 1, we got the C of t which is equal to 1 minus e to the power of minus omega nt of 1 plus omega nt. For this we got the output waveform C of t quite similar to input waveform. There is a small you can see a kind of small increase was there with a small rise time, and immediately the output is reached. Now this output is quite similar to the input. Now we obtain here the response which is fast in nature, or we can say the response is quick in nature. So for critical damped system, this is how we reach the output for step input. Now for the overdamped system, as we have seen in our today's class, we got the equation C of t which is the mixture of 1 minus fraction of these values. Now when you apply the waveform conditions, we have seen that the output waveforms is completely drooping in nature. The zeta as you go on increasing, it is reaching to the x-axis, and the response is also very slow. Hence, for second order system, when the input is step input, we got the output for undamped system as oscillations. Underdamped systems, we got the damped out oscillations. Critically damped, we got the output which is quite similar to the input. Whereas in overdamped system, we got the response which is very slow in nature. So this is how you remember the time time response analysis for second order system. Uh, that's all for today's class. I hope you like this particular session. Please share among your friends, subscribe to this channel and press the bell icon for the future notifications. Thank you.